Okay, so when, here's my function, when x is 1 I get 2, when x is 4 I get 17. The curve is something like this. And so the area that I want is when people say the area under the curve, they mean like this. Cool? It's a very likely shape. Okay, we want that area. How do we get it? Well, we're going to approximate it using rectangles. And we want an upper estimate, so we should use LRAM or RRAM? RRAM. We want to use RRAM. Also because it's just like a little, it's like 5% easier, but also because I asked for an upper estimate. Okay, so let's start drawing the rectangles. We are going to have n of them. So it's hard to draw like n of something. So you just kind of like draw one, draw another, and then just sort of like dot, dot, dot. All right, and then let's just skip ahead to like the nth rectangle. You guys with me? Yeah. And by the way, how wide is each rectangle?
Oh, no. It's the whatever the 4 divided by it. 3 divided by it.
Yeah, the width of the interval is 3, and if there are going to be n rectangles and the total width is 3, then the width of each one is going to be 3 over n. True. Okay, so this is, so what is this point right here? You're going to be a little careful-ish. 1 plus 3 over n. Next one, Wenson? Too slow, Brian. Yeah, but let's like write it for pattern recognition purposes. Yeah. Yeah, so says Wenson, dude, you start at 1, and then by the time you get here, it's like you've scooted over by 3 over n twice. Okay, next one. Brian?
What? 3 times 2 over.
But then also plus 1, remember, because you start at 1. So it's like 1 plus 3 times 3 over n. And this we could even write as 1 plus 1 times. Is everyone cool with me here? It's like you got to kind of dwell on it a little bit to feel what's going on. All right, we get to the end. It's the last one.
1 plus 1 times n, so it's like 1 plus n times 0.
Yeah. And notice that like that's just 4, of course. So that means that our logic's all like holding together. Okay, good. Now all I have to do is figure out what the areas of all these rectangles are. Doesn't sound too hard. Let's see. The first rectangle will have width plus 3 over n and height f of 1 plus 1 times 3 over n. And the second rectangle will have width 3 over n and height f of 1 plus 2 times 3 over n. And throw in some dot, dot, dots. The nth rectangle will have area, well the width is still 3 over n and the height is f of 1 plus n times 3 over n. Okay, so we have sigma notation. So if you feel comfortable, you can just go straight to the sigma notation. What is the area under this whole thing expressed in sigma notation, Elaine? Elaine says, dude, you just follow the pattern, right? Each time we skip over by a tiny bit, so that is going to be the general formula. All right. If you get that, it means that you understand exactly what's going on. You basically get the big picture. You understand how to like figure out, think it through and all that kind of stuff. Now it's just a matter of cranking this out. And we have only 4 minutes, so let's go. 3 over n times, I'm taking the sum from I equals 1 to n. Well, the only thing I can possibly think to do is plug that into my function, right? So I get 3 over ni plus 1, like squared plus 1. So I have to use the actual function at a certain point. Okay, let's like simplify this out. So this is 3 over n times. I think the strategy here should be to just to expand inside these brackets. So we can all square a binomial, right? What do we get? 9 over n squared I squared over n I plus 1, and then like plus another one. Okay, so plus 2. Okay, and now I think we should just split it up into 3 separate sigmas. Can you guys do this on one step? And then the final one would be like 6 over n times the sum of 1. So it's just, you just kind of do it, right? You're just splitting it up into 3 separate sigmas by just like, you know, splitting it up and then factoring things out. Alan, you cool? Alright, and now we reach for those formulas. So, okay, let's do it. 27 over n cubed times, what is the sum of from I equals 1 to n of I squared? N plus 1, 2n plus 1 over 6, plus 18 over n squared times, that one is n plus 1 over 2, and that one is 6 over n times n. So I'm just using the formulas, going a little fast, I'm sorry. Okay. Many cancellations are possible. I can make that n squared and kill that n. I can kill the 27. I can take a 3 out of the top and the bottom here. Here, that's like a 9. Let's look at that. Okay. So by being very careful with my algebra and using the formulas and canceling, I end up, when the dust clears, with 9 n plus 1 over 2n plus 1 over 2n squared plus 9 times n plus 1 over n plus 6. Great. And I'll even just do one more thing, which is to multiply out this thing here and get the quadratic 2n squared plus 3n plus 1 over n squared. Okay. All right. So that algebra happened a little bit fast, but I eventually get this giant thing. And now I want to talk about what does this giant thing mean? Yeah, don't bother getting a common denominator, it's not worth it. What is this giant expression in this box? What does it represent? Say it again louder.
The area you have n boxes.
Yeah, it is the area under this curve, approximately, from 1 to 4, using an overestimate, assuming, what does the n mean? Assuming that you have n rectangles. Crap, did we turn? Okay, well, we did now. Was it out of frame?
Yeah.
Oh well. Alright, yes, says Alice, this formula represents the area under the curve as estimated by n rectangles. In other words, this is like a formula. If I plugged in 10 for n, what would I get? Some number, which would be the area approximated by 10 subintervals. If I plug in 100 for n, then that would be the area as approximated by 100 rectangles. What number would you like to plug in for n? The biggest number ever. In other words, and now finally we do some calculus for the first moment, because calculus is all about infinity, we just take the limit as n goes to infinity of this entire expression. And if we do that, what do we get? What is this rational, what is this?
It's just
2. Careful, it's not quite 9/2 because there's also this, it's double up here, right? So it's just 9. This is, as n goes to infinity, 9, and this is 6. Okay, so this is 24. Whoa. The area under this curve is exactly 24, which is kind of shocking. All right, final note. This is integration. Integration is the process of finding the, loosely speaking, formal definition coming later, the process of finding the area under a curve as approximating it by many, many, many little tiny rectangles. All right, good. More on this tomorrow.